get familiar with these basic functions and their graphs. We're going to be utilizing this later on, shortly, throughout the course, especially towards the end when we analyze some functions and look at what we call end behavior. But that's it. 2.1 is just getting you familiar with this very simple thing of raising something to a power. And we call this like it's a natural power function. We're just going to call it power function for short. Okay, what do we do with power functions? Well, we can add them, add multiples of them together, subtract them together. We can combine power functions. So that brings us to the next section, because there's no homework problems for this. This is just introducing this idea. And in 2.2, we introduce something called a polynomial or polynomial function. So hopefully you get a sense for power functions. You just play around with it by plugging into your Desmos or TI-84, and you can see. You can keep plugging one on top of another, and you see the differences as you raise the power up. And again, these are just natural number exponents. Later on, we'll see a more general power function where you might have a fractional exponent, but this is just a natural exponent power function of a natural power function. But that will lead us to 2.2, which is all about polynomial functions. Well, sometimes we just call them polynomials. We say polynomials. Now, all they are is just a sum of the various power terms, power function terms multiplied by each other. So what is a polynomial? So here's our definition. A polynomial function is a sum of multiples, and the multiplication factor can be fractions, it can be integers, but it's multiples of the natural power function. This is power function, I'll call it natural, meaning it's a natural numbered exponent of the natural power function. That's it in Word. What does it look like algebraically? This is where some students get a little bit, lost a little bit, because it's the language of mathematics. So here's how we write it out algebraically. We take some number, a sub n, and then I take my nth degree power function. This n subscript doesn't mean anything, it just says that's the nth coefficient tied to x to the nth power, plus a sub n minus 1, x to the n minus 1, plus, and we keep counting downward to a sub 2 x squared plus a sub 1 x plus a sub 0. The a values are constants. So for example, this is an example of a polynomial function. 3x cubed minus 2x squared plus 4x minus 3. Here, a sub 3 is 3, a sub 2 is negative 2, a sub 1 is 4, and a sub 0, the constant term, that's always the constant term, is negative 3. That's all it is. Now you can be missing terms. Here's one example. Here's another example. So say I had my 4x to the 4th plus 2x squared minus 5. I'm missing an x cubed and an x term. That's okay. That just means those coefficients are 0. That's what it is. It's just a sum of multiples of the natural power function. And it has their coefficients that can be positive or negative. Doesn't matter. So that's our definition of a polynomial function, or polynomials, we'll call them. They come from polynomial expressions. So what is it we want to do? Well, we want to be able to analyze polynomial functions. We're just going to start now, but we're going to see some of the analytical techniques later on. So when we start looking at polynomial functions, the two things that are going to be important at this time are, like at any function, its domain and its range. So both of those we want to be able to understand. So let's start very simply. So now that we have our definition, let's start and look at some of the important ones. We're not going to go to the high-level ones, the high degree right now. We'll save that for a later date. And even when you get to the calculus, it doesn't get that crazy. We usually stay down, cubics and quartics, and sometimes we'll go to fifth degree, not very, very frequently. So let's start with the types of polynomial functions. The first type is what we call a linear polynomial function. And in that case, it's f of x is by a1x plus a0. Now, you're more frequently used to seeing it written this way. Alternatively, you've seen, f of x, we replace, that's the y values. This is an alternative way of showing it. Y is m times x plus b. That's the more familiar way you used to. They're the same. These are the same. A1 and m are equivalent, and a0 and b are equivalent. That's essentially my line function. Now, I want to make mention over here, for those that do go on, we're calling these linear polynomial functions. That's actually a lie. They really should be called, the correct name is really what we call affine functions. They're an affine function. To be truly linear, the a0 or the b would have to be 0. That's the only way to make it linear. Is if as long as that b constant term is there, it's not technically linear, it's really affine. But we use this linear because the graph of these are always lines. So we know that. We have that common sense notion of that. So for this example over here, and f of x is equal to 2x minus 3, where a sub 1 is 2, or its slope is 2, and its y-intercept a sub 0 is gamma negative 3. So that's where it is. What do we always do? We look for its graph. Well, we know how to graph lines. We've learned that in basic calculus. That's what we're going to do. Go back to what we know. So you should know how to graph lines. So down here is my y-intercept, negative 3. Go up 2 over 1. Here it is. Up 2 over 1. So this is a graph line. What are the two features we want? We want its domain and range. What's the domain? All real numbers. What's the range? All real numbers. This goes up to plus infinity, and this goes down to minus infinity. So y can be anything. How do I get that particular y? I plug in any number for x that goes from minus infinity to plus infinity. So again, domain, x is a real number. The range, y is any real number. Very simple. Okay. Let's take a look at the next class of polynomial functions. That's the simplest one. Those are the ones we've looked at, very basic algebra courses all throughout. So we move beyond the linear polynomials, and now we go into what we call quadratic polynomial functions. Okay, so there the general form is f of x is a2x squared plus a1x plus a sub 0. Or, again, your more familiar form of this is y is ax squared plus bx plus c. Means the same exact thing. Here, a sub 0 is a constant c, a sub 1, my coefficient in front of the x, we call that b. Yeah, either one of those are fine. But it's just a constant times the x squared plus a constant times the x plus c. Now, these constants can be negatives, they can be fractions, they can be anything. So let's take a look at analyzing, in the same way we did the linear polynomials, the quadratic polynomial function. And let me start with an example over here. We put the example, then I'll look at how do we analyze it. So let's take this as an example. So here's my f of x is equal to x squared minus 10x plus 2. Let's go to the graph of this. Now, I could put this into my calculator, but again, as I said, we're practicing completing the square. Let's kind of take a look at that. So here's an analysis of how I would complete the square again. I said we're going to be looking at this, so hopefully you're going to get proficient at this process for the end of the course. Complete the square method. What do? Well, if we're going to graph it, we call f of x equal to y. We're not looking for the inverse function now, so we don't have to swap the x and y. Stop yourself from doing that. Because this is no longer the inverse, we're just looking at trying to graph this function. So here, I'm going to complete the square of this. Completing the square does not involve swapping x for y. That's just rotating about the line y equal to x to get the inverse function of that, but that's not what we're looking for. So what do? Well, let's move that 2 over by subtracting it. So, well, we'll try that. I'm giving you this. I want you to complete the square of that. So instead of with a y squared over here and a y, we have an x squared and an x. Practice that. Complete the square on that and show me what you get. And we're going to see some certain features of this quadratic polynomial or quadratic function. So complete the square on that and tell me what you get. Y plus 23 is equal to quantity x minus 5 squared. Does anyone want to see how I got from here to here? Anyone want to see that? Okay, so let's kind of do this. First step over here, I'll subtract 2 from both sides. I'm going to subtract this 2 from that side and from that side. So I now have y minus 2 is x squared minus 10x, 2 moved over. I'm going to complete the square on this. So what am I going to do? I want to put this in this thing. So I have to take that negative 10, divide it by 2, gets a negative 5, and then I square the negative 5. I get a positive 25. That's what I'm putting right here. But if I put 25 on this side of the equation, I have to keep this in balance, so I have to add 25 to that side. That way it's the same expression. If not, then this side is 25 larger than the other, so it's not what I originally had. Well, 25 subtracting 2 is 23, so I'll just write that as y plus 23. The reason I added that 25 is because that can now be factored as x subtracting 5 squared. That's it. I completed the square on that. We'll do some more of these, and you'll kind of see how they shake up a little bit here. Okay. Question, Ashley?
So you're always going to take that last number, divide it by 2, and then square it?
Yep.
And then make it right on the other side. I understand.
You got to balance.
Yes. Okay. I think I finally got it.
The reason we do that is because you can see, you can factor that into, x minus 5, x minus 5, or really x minus 5 squared. We're making this factor so it's completing and making that a perfect square. And that's why I need to divide it by 2 to get that number. So I have my minus 5x and my minus 5x to give me my negative 10x. And then I have a negative 5 times a negative 5 to give me a positive 25 over here. But that 25 has to be placed on both sides to keep everything in balance. Otherwise, it's kind of think of it as a balance beam over here. These have to, if I add 25 pounds to both sides, I'm not changing and putting it off balance. I'm making them the same. Okay, so we can take any quadratic or quadratic function or quadratic polynomial function and complete the square. And we'll always be able to put it in this form. This is an example of that. So in general, I have the following. You can start with any polynomial or quadratic polynomial function. And I can rewrite it in the following way. I can kind of write it over here. Because I can move this 23 over if I wanted to. And you can complete the square. So you can take this function, and you can complete the square. And rewrite it in this way. F of x is equal to, and I'm going to put the generic coefficient of a times x minus h, quantity squared, plus k. Now this is the standard form, if you will, of a quadratic polynomial function. Now, these numbers, h and k, and as well as h, are important and they have a certain meaning. So let's take a look and explore that meaning of those. Meaning, let's show what I mean by that. Over here, I need one extra step over here. So to go from here to here, I have to subtract 23 from both sides. If I want to put it in this way, I subtract 23, so I get my y, which I'm calling f of x, is equal to my a coefficient for this one just happens to be 1, and my h over here is a positive 5, and my k over here is a negative 23. So I went through an extra step and moved that number over to the right-hand side. That's all I'm saying, that general form. I can do it with any quadratic. So this can be transformed into that. Well, I'm talking, writing, going back to the original. It should be a1 plus a0, but that doesn't matter. I could call it ax squared plus bx plus c. It doesn't really matter. Okay, so let me go and continuing on over here. And talk about what the h and k and a actually mean. So here again, I have my polynomial, quadratic polynomial function, ax minus h squared plus k. Well, what does a or h and k represent? Now, if a is positive, so I have a positive coefficient, then the graph of this looks something as follows. So I have my h k, so this is the point over here, and that's my x coordinate is h, my y coordinate is k. And if a is positive, this will always give me a parabola that goes this way. And we could show that. This h comma k is given a special name. This is called the vertex of the parabola. And it also gives me something here called a straight line through x equal to h. So this is my line x equal to h. That's called an axis of symmetry. Now, if a happens to be negative, so if a is negative, I get something very similar over here, but it just flips it. So say I had the same h and k value, say that was over here, had the same vertex, also the same axis of symmetry, because it's symmetry, it's like a mirror image on either side, but when a is negative, it goes downward. It looks something like this. Parabola going downward. The reason I state this is because this gives me information about the range of the function. We know that the domain of any polynomial function is going to be all real numbers. We looked at that, the power function. We just made up a power function. So the domain of any polynomial function is all real numbers. The range can and often is different. For the range of this one, that's my y coefficient, y is greater than or equal to k. The range for this one is y is less than or equal to k. You can kind of see now k can also be negative, so it can move anywhere here. This is just a generic thing. So what we want to do is we'll close out here in the last minute or so and just state that if you have quadratic functions, domain is any real number, but the range depends upon the graph. It depends upon you completing the square and doing the graph. So for quadratic, so f of x is equal to a times x minus h squared plus k. The domain for that is x is any real number. But the range for this one, it depends if a is less than or greater than 0, then the range for that is y is greater than or equal to k. If the range a is less than 0, then y is less than or equal to k. And we'll kind of see that. Okay, so let's stop. You can go to the next one, but I think we kind of worked it out here. Section 2.2 is on the idea of polynomial functions. And just a quick recap. Yesterday we introduced the basic linear polynomial functions, and we also did the quadratic polynomials, or quadratic functions, if you will. And there's others, as third degree, cubics, quartics, quintics, etc., all different degree polynomial functions. And you know what a polynomial is from your previous courses. It's just the largest exponent in that polynomial, and that's the degree. This is first degree, second degree, etc. Okay, so what I want to do is we've been looking at polynomial functions, especially the quadratics. We spent some time looking at those, how to find the vertex by completing the square. We'll do some more of those today. I'm sure you'll have questions on that, because there's some variations that we didn't look in great detail about yesterday. But what I want in that section is this whole thing talking about the domain and absolute max and mins, which were on the homework, but I said, we hadn't quite covered that yet, so kind of, if you didn't get it, that's okay. But I want to now look at the textbook where we talk about the domain and range of these polynomial functions. They actually align themselves in a very basic way. Just by looking at the degree, whether it's even or odd, you can determine something about the range. The domain is an easy question, and we'll answer that first. Okay, so let's go to the textbook over here. I'm going to just share my screen over here. We'll just kind of work it through there. So here's the textbook, and here's the domain and range of polynomial functions in general. This is on page 43 in the text. Now, this is true for any polynomial function. The domain is the set of all real numbers, no matter what polynomial I'm dealing with, whether it's a linear, quadratic, cubic. Why is that? Well, you can put in any number into your polynomial function and get a real number out. There are no problems with picking a specific number that's going to cause difficulties, such as the square root problems at square root of a negative or dividing by 0. So that's an easy question. Polynomial functions are easy in their domains. Okay, so we can kind of move on from that. Now, we're going to define two different things that are related or will be related to the range, something called an absolute max and an absolute min. So the first definition there is an absolute maximum value of a function is the largest y value. That's the max or min is in terms of the y's, if there is one. Sometimes there are no absolute max and mins. And the value that the function obtains on the interval as x goes from minus infinity to infinity, meaning the entire domain of the polynomial function. And by largest, the absolute max is greater than or equal to y for all the other y that are in the range. In a similar fashion, we have an absolute min, where it's the smallest value. So very similar throughout the range. Okay. Throughout the domain, excuse me. Now here's some interesting things. If the degree of a polynomial function is odd, then it's easy to determine the range. So if it's a first degree polynomial function, a third degree, fifth degree, the range is always going to be the set of all real numbers. Because you can pick at x, any x value, and you can get any y value by choosing the appropriate x from minus infinity to plus infinity. So in polynomial functions, an odd degree polynomial, domain and range are both all real numbers. X can be any value, y can be any value. Where it becomes problematic is when we start dealing with the even polynomials, even degree polynomial function. And here's a little theorem that talks about it. An even degree polynomial function, first off, will have either an absolute max or an absolute minimum, but not both in its domain. That's one of the things. I'm not going to prove these theorems, these are beyond the scope, but they help us in analyzing things. Now, if it's an absolute max or an absolute min, it's going to depend upon the sign of the leading coefficient. We state that in the theorem here below it. So if, again, the polynomial function is even degree, and if the leading coefficient, the one that's in front of the largest degree term, is negative, then the upper limit of the range is the absolute max. That will have an absolute maximum. And if the leading coefficient is positive, what we're going to find is it's going to actually have an absolute minimum at its lowest point, and then on both sides it will go up to plus infinity. And we'll kind of show this and illustrate this, but I just want to kind of go through these theorems that allow us to analyze these polynomial functions quite simply and easily. Okay, instead of writing that on the board, I just wanted to save the time here and just put it to you that way. It saves me a little bit of time of writing, and then we can actually go to working some problems. So that being said, we now have about everything we need to know or want to know about these polynomial functions. What's left missing is practice. We now have to get a sense for that. So you have it in words, but you want to understand it more in detail. So let's go to some homework problems. This is where we'll actually be analyzing, especially when we deal with some of the quadratics, and go through that. So anybody have any questions on the homework? Let me get it up on the other screen over here so I can see it as a question. Okay. Any questions on the homework in 2.2 about finding that? So number 13. Let me get it up here so I can see it. Okay, so this is a cubic, so we can analyze that very easily. That's not a lot of work there. So find the domains and find if it has an absolute max or min. So number 13. So again, we want to find the domain, the range, and if it does, it have an absolute max or min. That's what we're asking. Since this is a odd degree polynomial function, so my f of x looks like this. So it's a negative 2x cubed plus 4x squared minus 2x plus 9. Now, later on in the course, we're going to analyze this in greater detail. When we get to chapter 11, we're going to be looking for local maximums and zeros. Right now, our focus is mainly on domain and range. Okay, first step, domain. It's a polynomial. So the domain here is all real numbers. So x can be any real number. Very simple. This is an odd degree polynomial. We just had that theorem. If it's an odd degree, I just said that the range for this, if it's an odd degree, is the y also can be any real number. Or if you want to do it in the set builder notation, you could say that the domain is a set of all elements x. X is a real number. That's all it is. And the range is set of all elements y, such as y is any real number. They should get used to the various ways of writing it. Another way of writing it is you could simply state over here that the range of the domain over here goes from minus infinity to plus infinity. Y is also minus infinity to plus infinity. Or you might say that minus infinity is less than x is less than infinity. These are all different ways of kind of illustrating the domain. Minus infinity is less than y is less than infinity. So if it's the domain, it's about the x coordinate. If it's the range, it's about the y coordinate. But this is easy. Odd degrees, polynomial function, very simple. Odd degrees do not have an absolute max or min. So you don't, once it's odd, you don't even have to answer that question. There is no thing, because something like this may look, if I looked at the graph and plugged it into my computer or calculator, I don't know what's going to happen in here, but it may do something like this. It may come down and go like that, and do something like that. I'd have to fill in some details so I could plug it in and see. This is not going, this goes down to minus infinity and up to plus infinity, so it does not have an absolute max or an absolute min. There is no finite value for its maximum, finite value for its minimum. That's all it is. Okay, so 13, any odd degree polynomial is an easy answer, or easy to answer in this case. Any other questions? Anything that might have a, even degree that you might want to, and all the ones that are odd degrees, it's the same answer. It's relatively basic and easy. So anything else? Any other questions in that section there? So number 9. Okay, so here we have now a quadratic. And again, we're asked to address the same sort of questions. Domain, range, and then absolute max and mins if appropriate. So let's put that in, number 9. So that is f of x is x squared plus x plus 5. Okay, this is an even degree. Well, first off, I should say the domain is easy. It's a polynomial function. So the domain of any polynomial function is that x can be any real number. All real numbers. No matter what I put in here, it's never going to be undefined. The range is a little more problematic. So what we need to do is we want to go to the process of completing the square. So we want to complete the square. But as I said in the end of chapter 1, we will be doing that often. So hopefully you get good at this. The easiest way to deal with that is replace the f with the y. Okay, so I start with this and I say y is equal to x squared plus 3x plus 5. First step over here, I'm going to subtract 5 from both sides. I move the 5 over. So I end up with y subtracting 5 is equal to x squared plus 3x. Now this is where I'm going to complete the square. Now I'm going to be dealing with fractions now, that I haven't been dealing with before. So what do? I take 3, divide that by 2, and I square it. So in that case, that is equal to 9 quarters. So I'm going to place a 9 quarters on this side, but I have to balance it. Whatever I do here, I don't want to change this. I'm going to add the same constant over here. By doing that, this now factors into a perfect square. I can now rewrite the right-hand side with parentheses as x plus, well, that 3 halves quantity squared. If I multiply that out, I'd have x plus 3 halves times x plus 3 halves. I'd have 3 halves x plus 3 halves x gives me 6 halves x, or 3x. And then I'd have 3 halves squared, or 9 quarters. Then I just do the simple algebra over here. Multiply top and bottom here by 4 to make them quarters. So I have 9 quarters minus 20 quarters gives me y subtracting 11 quarters. So it's y minus, combining those two gives me 11 quarters. Okay, so let's put that on the side over here. This is my final form that I'm going to be dealing with. Y minus 11 quarters is equal to x plus 3 halves quantity squared. Now, we can get a sense for what this parabola is. This is all these quadratics. The graph is always a parabola. And since the coefficient in front of the square term is positive, it opens upwards. So if I want to go to a graph, I could put it into my calculator or my computer, but I'm just going to do this, by hand over here. Sense what this looks like. Okay, here's my x, here's my y, and what happens here, let's go to where this occurs. The vertex over here, I'll put that information here, the vertex occurs at the negative of that number in the parentheses, so x is equal to negative 3 halves, and the y is a positive. It's always y minus, so it's equal to y is equal to 11 quarters. So if I put that in, I go say here's negative 1, 2, so coming over here, let's kind of put it over here, and I go down negative 1, negative 2, negative 3, and I could put the vertex over here. Here's negative 8, 9, 10, 11 quarters and 3 halves. So it's right about here. That's where the vertex is. And its coordinates are negative 3 halves for x and positive 11. Keep me awake. Positive 11 quarters. Keep me awake. So right about here. Or 8, 11. So right about there. So that's where it is. It's by -3/2 for x and a positive 11/4 for y. It's going to open upwards. Now I know if I plug in, if I go back to here and I plug in 0 for x, so I'm on the y-axis, my y-intercept is 5. I'm going to pass through this point right here. It's going to look something like this. It's going to have a symmetry based upon that. This line right here that passes through the vertex, this vertical line here, that's my axis of symmetry. And that occurs at x is equal to a -3/2. When we have this picture, we can then start dealing with the range. Now we can see the range of that function, because it's all the possible y values. From this picture, we can see very clearly that it has a range that y has to be greater than or equal to 11/4. I'll never get a y beneath that. So I can then talk about the range over here. No, you don't switch the x and y. That is when you're finding an inverse. So that was different. You do not swap x and y. We're not finding an inverse function. We're just analyzing this function, not its inverse. Yes, if we were finding an inverse, we'd switch the x and y, complete the square, and then we get the inverse function, which has a square root involved. Because the inverse of the square is a square root, as you find out. No, good question, because I know that's going to cause confusion because you just did that. Understand the context of what we're trying to obtain right now. We're just trying to take this function as it is, not find its inverse, find its domain, its range, and see does it have any absolute max or mins. But the range over here we can see. The range is the set of all elements that y, in this case, is greater than or equal to 11/4. And you can write that in more sophisticated notation if you wanted to. The range is a set, y such that you very specific. Say y is a real number and y is greater than or equal to 11/4. Or I can be a little more informal mathematically. Now the next thing, we move on to absolute max or mins. Well, there is no absolute max. This thing just goes off to plus infinity, but it does have an absolute min. There's a point on this graph where I can get no further. So it has an absolute min. So every even degree polynomial, as that theorem says, will either have an absolute max or min. If it's an odd degree polynomial, there are no max or mins. The domain and range is all real numbers. But it does have an absolute min. And the value of that minimum, value is y is equal to 11/4. Now it occurs, that's why sometimes students get confused because they use the x coordinate and someone says, what is the absolute minimum value? The absolute minimum value is the y value. Now it occurs at the point -3/2, 11/4. But when you're asked what is the absolute minimum, it's 11/4. It's not where it occurs, it's the y value. So be very careful about that. That's the minimum value. That's just the vertex at which it occurs. X has nothing to do with the absolute value, the minimum of the absolute value, or the maximum, if that were the case as well. It's just where it occurs. So when the question asks, what is its absolute minimum? There it is. It says, where does it occur? At that point. Little subtleties in the language of what's being asked, so make sure you're comfortable with that. Okay, so that's where things get a little more interesting. If it's a linear, cubic, fifth degree, etc., domain and range is simple. If it was a second degree, fourth degree, sixth degree, it gets a lot more complicated. It's a lot harder to deal with. Okay, let me see if there's another one that might be of interest. Well, in this case, it's asking, what is the absolute max or min? This has no absolute max. It's infinity. Infinity is not a number. It's a limiting process. So in this case, as it said in that theorem, if it's an even degree polynomial, it'll either have an absolute max or an absolute min. Can't have both. It will have one or the other. Now, when you get to calculus, we're going to be looking for local max and local mins. That's why I want you to get familiar with this, because you're going to be mixing in calculus with absolute maxes, local maxes. So get a good handle on this. So when they start distinguishing what a local max and min are, then you say, oh, okay, now since I know absolute max, I can just make a slight adjustment and I talk about local max and mins. That's where it gets really important in the calculus. That's why I want you to have a thorough understanding of functions, like this, and all their basic properties. But once I find an absolute min, I don't even look for an absolute max. And what happens? This goes up to plus infinity. It never gets, going up to infinity. It never reaches here. Coming down, it reaches a minimum value, and then it starts increasing after that. If a slight change over here, if you had and put a negative, well, let me do it. If I put a negative out of everything, that's something that was just negative like this. And it would actually come down. It would actually come down beneath over here. Look more like this. It would take it over here and bring it right about there. It would look like that. It would end up having the same axis of symmetry, but its absolute max now would be negative 11 quarters. So the blue one is without the negative sign, and the green one is if I put a negative sign. It would flip it all the way down that way. And this has an absolute max, but no absolute min, because it goes down to minus infinity here. Where both of those go up to plus infinity. Let's take a look at another one, just to kind of clarify this. So any other problems in there? Maybe I should pick one out. Might be different or interesting. Now, the first problems, you see problems 1, 2, 3, 4. Those are all lines. Linear polynomials, their domains and ranges are just plus and minus infinity. All real numbers. They also do not have an absolute max or min. Why? Because it's an odd degree. First degree, 1 is an odd number. So in that case, those are easy. It's only problems 5 through 11 that you have to worry, is it an absolute max or an absolute min? And there's one in there, so let's take a look at number 6. Take a look at number 6. It's written in a slightly different way, but let's analyze that one. The square has already been completed for us, so it's not so bad. Now take a look at number 6 over here. So we have f of x is equal to minus, so f of x is equal to minus, the 3 out front. 3 times quantity x, 2x minus 3 2x minus 3 squared minus 7. Okay, this is already in the form. Let's just replace the f of x with y. So I get y is equal to minus 3 times 2x minus 3 quantity squared minus 7. Then I'm going to put it in what we call the standard form. The standard form is always this. Y subtracting k is equal to a times, x minus h quantity squared. This has the coefficient in front of that, so we have a little bit of problem. We have to find out when that is 0. I have to kind of divide that out, if you will. So this is slightly different than the standard form. And I'll show you what we would do to make that happen. It might confuse you a little bit, but what we do is you just set that equal to 0, and that will give you your h value. But I'll put it in here. So first step is let's move it over. So the negative 7 comes over as a positive 7. Well, I'm going to show you where the vertex is. Let's just see where the vertex is. So I get y plus 7 is minus 3, 2x minus 3 quantity squared. Now, notice I have a coefficient of 1 over here. I'm getting my k. I can see my k directly. My k is a negative 7, not a positive 7, because the formula already has a negative sign built in. Now, I don't have a 1 over here, but what can I do? Let's take a look at that separately. So I have 2x minus 3 quantity squared. Well, I could factor a 2 out of those. So I could write that as a 2 times x minus 3 halves quantity squared, right? All I do is I pull the 2 from the x, but I had to pull a 2 from the 3, so I have to write that as minus 3 halves. This 2 can come out as a 4, because that comes out as a 2 squared times x minus 3 halves squared. So it's really 4x minus 3 halves quantity squared. It's all in the algebra. So I could rewrite this in the following form. Y plus 7 is minus 3 times this 4, so that gives me a minus 12 times x minus 3 halves squared. This is doing it alone, and then I'll show you the shortcut for doing the same result. This is now in the standard form, so I can say over here my h, it's always the negative of that, my h value is a positive 3 halves, and my k value is a negative 7. That's where the vertex occurs. Now, if you don't want to do this over here, if you don't want to put it up, make it look exactly like this, here's the shortcut that you can do. All I need to do is set that equal to 0, and that'll give me my h value. So I set 2x minus 3 equal to 0. I get x is equal to 3 halves. That's where the vertex occurs, right here. But you could go through and formally make that look exactly like that. And then I pick out my numbers, h and k. Okay, so we're part way there. Let's get rid of this. That was an aside over here. Let's now thoroughly analyze this and see what's happening over here. So I'm going to go to a graph. Now this is where, you can put this into your calculator, but I would suggest you try and sketch these out by hand yourself. Okay, so let's kind of put everything in over here in terms of a graph. And let's put in that vertex. Yes, Yaska.
Would it be a negative 12 in front of the binomial?
Because when I rewrote this, this is equal to negative 3, and I pulled the factor of 2 squared, or 4, out of there. Remember, just if you look what I just erased, there was a 4 over there.
Okay.
And then I take the negative 3 times the 4, and I got a negative 12. When I rewrote this, you see that now?
Yeah.
Okay, that's a question. Yeah, that's all it is. A simple little algebra there. But that's what you would get in that regard. Okay, so now we come over here. And my x-coordinate, I'm going to go to 3/2, and that's -7. So, in fact, let me redo this just slightly because it's going to go downwards. So I really want to be raising that upwards. I want that to come up a bit higher. Let's do it up here. Okay, and now let's plot that. The vertex is at the point x is 3/2, y is -7. Okay, so I go over here, 1.5, and 1, 2, 3, 4, 5, 6, 7. So right about there. That's the vertex. That is also the axis of symmetry. Passes right through that vertex, and right through x is equal to 3/2. And I'll put the coordinates of the vertex right here. Now, let me take a look at this. There's a negative coefficient. If you have a negative coefficient, of course y has a positive in front of it. You have to be careful. Make sure the y has a positive and it's on that side and that has a negative. We know it's going to open downward. This is a parabola that will open downward. And if you're not sure, you can plug it into your calculator or Desmos or whatever, and we'll work out. Now we could, if we wanted to, let's find out what the x-intercept. I'm not asking that right now, but we will be asking that at the end of the course. Let's see if you can evaluate this. So let's start with this over here. This gives us some practice of what we did in chapter 1. Can you tell me what is f of 0? Do that evaluation for me. Plug in and get f of 0. Give me a second to work that. And quickly do it in my head, and I get this. If anyone wants to see that, I'll be happy to work it. What it says is my y-intercept is way down there through the floor. So this will kind of go straight down that way. And eventually, at -34, it will cross the y-axis. Does anyone want to see how I obtained this? Just raise your hand or chime in or something. Okay. So all I'm going to do is plug in 0 in my f. So this is what we did in section, I think, 1.3. So f of 0 is equal to -3 times 2 times 0 minus 3 squared minus 7. Okay, so that's equal to -3 times, well, 2 times 0 is just 0, so it's -3 squared minus 7. That's -3. -3 squared is a positive 9. Then -3 times 9 is -27 minus 7 is a -34. And when x is 0, the y, f is a y value, so this is a y value that I'm eventually finding. So I'm finding the coordinates x is 0, y is -34, which happens to be the y-intercept, way down beneath the floor. Now, we will not be doing this analysis until the end, but functional evaluations get comfortable with that. Okay, so now we can start answering some of those questions. What is the domain? Easy. It's a polynomial. The domain is x is any real number. What's the range? Well, that's a little bit different now. Notice I will never have a y value above -7. So I'll write it out. We have the domain is x is any real number. With the range, we have is y is going to be less than or equal to -7. Does this have an absolute minimum? No, it does not, because both of these go to infinity. Does it have an absolute maximum? Yes, indeed it does. It occurs right at that vertex there, and its value is -7. So it has an absolute max, and it's equal to -7. Again, it will have either an absolute max or an absolute min, not both. So you can see how to analyze these things to find the domain, range, max and mins if it's an even degree. Odd degree, no absolute max or min. You don't even have to look. And you get that by understanding the various power functions and how they dominate everything. Okay. Does this help a little bit more, hopefully? I want to make sure everyone understands this because we're going to be looking at, next time when we look at radicals, it gets a little more complicated. So we want to have at least this level down. Finding the domain, the range, and in this case we're looking for absolute max and mins. In chapter 11 we'll put it all together with all the different types of functions we're going to look at. We're going to look at a lot of different functions here. It is complicated. I've cut out quite a bit of material because, you know, this course normally has so much thrown in it. So I had to try and streamline it so I could fit it into a nice sized book that we could do in a single semester. That's why I kind of, you know, carefully chose things. And I teach all the calculus, so I know what's needed. So it's like anything, the first time you see it, it's a little fuzzy. Then you go work a few problems, it starts to get a little clearer. Then we come back the next time, I work the problem again, and then it starts making more sense. And then you go and look at other problems until you kind of fully master it. It's just repetition, a lot of repetition. First time it's always fuzzy, for sure. Unless you just suddenly, everything just makes sense to you instantaneously, but then you're the rare person. You can probably just educate yourself and you don't even need to go to college, like some people do. Okay.